basically a hands-on experiment. So many of you who are interested in this working out on superconducting qubit, that's the place to go. So I would not add much because you will see his work. You can go to your site. Enormously successful researcher, and more importantly, for the first time in India, I think for the first time, right? Superconducting qubit, making the circuit superconducting qubits and getting results from there. I don't see anything from India has emerged in that experimental front except from your group. So, okay, so now it's 50 plus 10 minutes kind of format. You can take your time, no problem.
Okay, great. Thank you. Thanks a lot for the kind introduction, Prashanta. It's a pleasure to be here. I'm glad to see that this series is continuing year on year, and it's being such a popular subject around the world. It's great to see that we are forming our own series and workshops, which are picking up and carrying forward. Yeah, as Prashanta mentioned, indeed, ours was the first superconducting qubit group in the country, but we now have actually two more. There are two new labs in IISc Bangalore, headed by Professor Vibhor Singh, and then more recently by Professor Baladitya Suri. Both of them are working on superconducting qubits as well, and are supported by various funding agencies, including DST's Quest program, which is one of the, I think, partners for this workshop as well. So let me share my screen. Okay.
Yeah, it's visible, perfectly visible.
Okay, great. Sorry, I'm just trying to hide this panel. Okay, great. Yeah, so I mean, today I'm going to really just give you an introduction to this field of superconducting circuits and how one can build qubits out of electrical circuits, and how does one control them, and how does one measure them, and then towards the end sort of mention where this field is going. So it's going to be a broad introduction to this field. I've kept things very basic and simple, and so that everybody is able to get a good flavor for what it means to work with these kind of systems. And then, of course, you can look up more. There's a lot of resources available online these days, especially from IBM's QIQT series and things like that. So I hope this will serve as a primer to more detailed resources you can find elsewhere. So in this workshop itself has been going on for some time, so I'm sure many of you have heard some of the very basics, but for completion, I'll go through them again. Oh, sorry, one other thing, I've just been having some allergies, so I might sneeze a lot suddenly and uncontrollably, so I apologize in advance for that. I will try to mute myself as much as possible. So a qubit is essentially a quantum two-level system. You can build it in many different ways, as we will see in a little bit. And it's, the name qubit is basically a short form of quantum bit, and bit comes from how we think about digital information, that there are two states involved. In the classical things, we call them 0 and 1. In the quantum case, we call them, QET 0 and QET 1. This is just to signify the fact that these are now quantum states. And that has an implication that you can now create superposition states of these systems, these two states as well, which is not possible in our conventional classical way of doing computation. So this is the main difference between classical computers and quantum computers, that you have the ability to create these superpositions. And I've written the superposition in a particular way, where these coefficients have been parameterized using these variables theta and phi. And this helps you to represent this state on a sphere. And that's a nice way of visualizing that all the points on this sphere are valid states or valid superposition states. We usually call it a unit sphere because the state, the coefficients mod square has to be normalized to 1 because, as you know, they represent probabilities. So this is a sphere of unit radius, and the points on the two extreme poles are the eigenstates 0 and 1, and then any other point on that sphere is a valid superposition with the particular value of theta and phi. So you can have the ground state, you can have the excited state, you can have an equal superposition state, which is exactly midway between the two. But you see that both the phi also plays a role, because this vector can point anywhere along this, sort of on this equator. So another way of thinking about it, it's like a latitude and longitude. So you have infinite number of superpositions you can actually create using this quantum two-level system. And this often leads to this idea about how much information can you really store in a qubit, and this is often a point of confusion. Turns out that even though you can sort of encode this state, this system in infinite number of ways, it really doesn't amount to much more information than effectively a single bit. And the reason is that when you measure these states, you get probabilistic answers, right? So if you start with an equal superposition state, which is on the equator, and if you measure it, you will get the answer 0, which also means that the system will end up in the state 0 with a certain probability mod alpha square if this was the state. If this was a 50-50 superposition, it will be a 50% probability. And if you can also get randomly the answer 1, and the result being that the state also ends up in 1 with a different probability, and the sum of these two probabilities has to equal to 1. Right? So even though there are infinite ways of encoding it, when you measure, you only get an answer 0 or 1, which means effectively 1 bit of information. Okay, so just having a single qubit with the possibility of the superposition is not enough to do something interesting or more than what you can do with a classical computer. What you need are many more qubits and the ability for the qubits to interact with each other. Okay, so if you have n classical bits, you know that it has 2 to the n possible configurations. But when you store something, you only store 1 of the 2 to the n possible states. Right? And when you extend this idea to qubits, now you have 2 to the n possible basis states available. But you can now create a superposition which includes all of those 2 to the n possible states. Right? So this is extending the idea of superposition to now many, many qubits. And this suddenly starts showing you something much, much more significant, that you are now playing around with a much, much larger number of states. We often call this much larger, the Hilbert space. There are 2 to the n states, and your entire physical system of n qubits could be in a superposition of all of those 2 to the n states. And this number grows very quickly. You might have often heard that even a modest n of 300, n equals 300, 2 to the n is more than the number of atoms in the visible universe. So this number can grow very quickly. And to imagine manipulating a system where all of these states are present in a superposition is really what gives the different possibilities and power to a quantum computer. And an algorithm essentially is just carrying out operations and manipulating this gigantic Hilbert space. And then at the end, you carry out measurements. And remember, there are n qubits, so you can carry out n measurements and you'll get n bit of information. But the magic has to happen in this algorithm, because at the end of the day, you still only get n bits of information. So because these are wave functions, one can have situations where the different states interfere with each other, and the fact that you are manipulating such a large space. So the idea of parallelism interference has to be exploited, and when you construct your algorithm. So you start with some n qubits in some initial states, then your algorithm evolves the system towards some final configuration, which hopefully gives you the correct answer to the problem you're trying to do with these things. Right? So that's sort of a very simplistic picture of what happens in a system. But in order to do this, you need to have physical systems which do that. So if you summarize these requirements, you need some physical two-level systems. It could be built in many different ways. You need the ability to put these systems into different superposition states. You need to be able to control them so that you can create the superposition state you want, whether you want to be on the equator or halfway around there or pointing in a different direction. So that control need to be able to measure it very precisely at the end of your computation. And in more advanced scenarios, if you want to use something called quantum error correction, and I'll mention that towards the end, you even have to measure in between to actually capture errors and correct them. And then very importantly, you need these qubits to actually interact with each other. Just having a collection of qubits which are not talking to each other doesn't do you much. And this is equivalent to doing logic gates in classical computing. So just like an AND gate needs two inputs to create an output to do a logic operation, similarly, you need to do operations involving at least pairs of qubits. So it's possible to do gates involving more qubits, but it's shown that if you can do at least with pairs of qubits, you can actually approximate any operation you would like with fairly high accuracy. So this is also important, and this requires some kind of a physical interaction in most cases between the objects which are your physical qubits. And then while doing all of this, you need to face two challenges. One is finite quantum coherence. This is the idea that these systems are not stable. You prepare them in some state, but over some characteristic time scale, they will lose that state. They will either relax to the ground state, or they might lose their phase information. We will discuss some of these ideas in more detail a little bit later. And then, as I mentioned, you need sufficiently large number of qubits for this Hilbert space to get big enough to start becoming useful. And this, these two things is what people are trying to improve. The last decade has been a lot of progress, both on the coherence front and on scaling to large number of qubits in a practical way that you can actually use these systems. And I'm sure many of you have seen what is often available in the news, the number of qubits people are now. We have reached of the order 100 qubits in many systems. Okay, so as I said, you need some physical system to encode these qubits, and there are many different ways of doing this. Some of the earliest experiments were done using trapped ions. The picture here is basically showing you two ions which are trapped in a vacuum chamber using electromagnetic fields, and they are fluorescing because we are shining lasers on them, and they are re-emitting that light. And you can now use the lasers also to manipulate the electronic states of these things, which are used for encoding the ground and the excited state. And then you can do all the operations I mentioned. This was some of the early experiments in individual quantum systems. More recently, we've had also the ability to manipulate single electrons, but not as sort of free electrons trapped in a vacuum chamber, but as electrons, effective electrons in a two-dimensional electron gas. With the help of electrodes, you can confine an effective electron in a small area, and then you can use the spin of that electron as your qubit. So meaning that the spin up and down corresponds to your ground and your excited state. There is a magnetic field, and these two states have different energies, whether they're aligned or anti-aligned. And then the topic we'll be discussing today is superconducting circuits. These are electrical circuits made out of superconducting materials, and these also have quantized energy levels which one can use, and we'll discuss that in more detail. And the thing is, all of these can be used to create some effective multi-level system, where typically you choose the two lowest levels as your basis states for your qubit. And they're all equivalent in the sense of storing and processing information, but they all have different properties when it comes to how much decoherence they have, how easy it is to couple the qubits to each other, how easy it is to create the superposition state, how easy it is to measure. So those metrics I mentioned just a couple of slides back, they all differ in these. And currently, trapped ions and superconducting circuits are sort of leading the race in terms of the most advanced demonstrations and systems. But semiconductor quantum dots are catching up quite rapidly. And there are, of course, many other platforms, including using photons, cold atoms, and topological qubits and NV centers in that, which all have their own pros and cons. And it's really open. I would say that it's entirely possible that some other physical system out of this list, or a new system which is yet to be discovered, could suddenly become the front runner in the next few years. So, in that sense, the field is still quite open, though a lot of progress has been made in trapped ions in superconducting circuits, and there's a roadmap for building larger and larger systems using that. Okay, so let's now focus on the superconducting qubit. And yeah, I just want to say at this point that if you have questions or doubt, feel free to interrupt. So I don't know, Prashanta, have people been asking questions in between, or usually you have been waiting till the end? Hello? Yeah. Okay. All right. So yeah, feel free to stop me and ask questions. So. Okay. So let's now talk about what the superconducting qubit is. So it's actually a very simple system, and it's analogous to a pendulum, except that it's an electrical circuit, and we will see how that connection comes about. So a pendulum is an oscillator, and we can associate an energy with the oscillation. And what the superconducting qubit looks like is shown here. This is a particular type of superconducting qubit called transmon. I'll explain that in a bit. But what we are seeing is an electrical circuit made out of aluminum on a silicon chip. And you can see the size of this. I've sort of put this here to contrast this to the size of, say, a typical atom, right, in trapped ions. So this is quite big. It's almost millimeter in size. You can see it with your naked eye. And yet it behaves quantum mechanically under the appropriate conditions. Okay, and what you're actually seeing are these two big squares. These you have to think of them as two plates of a capacitor. And then in the middle, there is this loop here, and there are these two areas I'm pointing right now. Let me use the laser pointer here. So this region here and this region here, they form a device called a Josephson junction. And you just have to think of it as some kind of an inductor. Okay, so what this really is a circuit which looks like this. The cross represents the Josephson junctions. There are two of them in a loop. And that only is a detail which allows you to tune the inductance by applying a magnetic field. And it is shunted in parallel with a capacitor. So this is a simple LC oscillator, which many of you have studied in your undergraduate courses or labs, maybe even earlier. And this has a resonant frequency. The reason this is similar to the pendulum is that the inductor is not linear. Just like the pendulum is actually not linear. Even though often when we study the pendulum in high school or later, we do a small angle approximation where we say theta, sine theta is theta for small angles, and we approximate. But that sine theta is actually the term which gives you the nonlinearity. And this is exactly the same form of nonlinearity here, that the effective restoring force, which in this case is related to the current flowing through this device, is proportional to sine of a quantity called the phase difference across these junctions. Okay, so that's a detail, but I just want to say that that's the same form of nonlinearity you have. So how is the qubit actually formed? The qubit states are basically oscillations of this nonlinear system with different energies. Means that state 0 is oscillator with 0 quanta. This is the smallest energy the system can have. Of course, you know that in quantum mechanics that there is you still have half a quanta of excitation. So we will ignore that for the moment. But essentially, the lowest energy state, which is the oscillator with 0 quanta, is called state 0. And then the state with just one extra quanta is called state 1, right? And there are actually other states higher than this in energy. You can have states with 2 quantas, 3 quantas, and so on and so forth. But we choose the 2 lowest levels, and you'll see a little bit more in detail. And that's it. This is what a superconducting qubit is. In the most cases, there are other kinds of qubit designs where this picture is not exactly correct. But essentially, it's a nonlinear oscillator. When it is in its ground state, which means it's not oscillating, it's called the state 0. And when it's oscillating with the minimum possible energy it can, so because in quantum systems you can only add energies in quantas, that's called state 1. Okay. So here is actually the potential energy diagram. So some of you who are familiar with LC oscillators and connected it with the harmonic oscillator, we have a potential which is a parabola, but here the potential is cosine, and that is because of the nonlinear nature of the oscillator. And these are the different energy levels which are part of the system. And the important thing is that because of the nonlinearity, the level spacing is not equal, which would be the case for a harmonic oscillator. And that allows you to use the two lowest levels just by frequency selectivity, because the energy difference between the ground and the excited, which means the electromagnetic radiation I need to excite the system, omega 01, is going to be different than omega 12, which is the excited difference between the first and the second excited state, right? So a typical transmon can actually have 3, 4, or 5 levels, depending on the exact value of inductance and capacitance. But we use the two lowest levels, and this is how we're able to make a qubit out of it, even though it's a multi-level system. Okay, but there are other conditions which are very important to get this qubit to work properly. And the first is that you have to go to very, very low temperatures, especially to temperatures such that the thermal energy is much smaller than 1 quanta of energy in the system, where here omega r is basically the resonant frequency of this oscillator, which is, you know, that for a LC oscillator, it's 1 over square root of LC. And that's approximately equal to this omega 01. There are some small corrections to that, but for all practical purposes, that's the value. So you need to go to very small temperatures. How small? Typically, these oscillators are have a frequency in the gigahertz range, you know, a microwave range of about 5 gigahertz. If you turn that into an energy using h bar omega and then divide by k Boltzmann, you get a temperature of 250 millikelvin. This is a very small number. So you have to go to much, much lower temperatures so that thermal energy does not excite your system. Right? And these kind of temperatures are achieved using a machine called a dilution refrigerator. It's a commercial system, and you can use this to get to these temperatures. It uses helium as a working fluid. And so you need to go there to achieve this condition. And the reason is that you don't want thermal energy to randomly change the state of your system. You want to precisely prepare the state and change it according to your quantum algorithm and not due to some random process. So this is very important to achieve. Also, these systems are, of course, made using superconducting materials. And as you know, superconducting materials can pass a current without any dissipation. This is equivalent to saying that your oscillator has very, very low friction. Ideally, you would like zero friction. And the reason is that when an oscillator has friction, it will stop oscillating after some point of time. So that is like saying that if I put the system in the excited state, you know, which is state 1, if it stops oscillating, which means it has dissipated its energy due to friction, then it has come back to state 0, and it will happen in some random time scale, and that's bad, right? You don't want it to change. But of course, it will happen on some time scale. So you want to maximize that time scale. So you want to have the smallest possible dissipation. So you use superconductors. So as I said, these are made out of aluminum typically, and that has a superconducting transition temperature of around 1 Kelvin. So this 10 millikelvin is much, much below that. So, so you need to get the superconductivity, but you also need to go to much, much lower frequencies, temperatures, so that you are able to satisfy this condition. Often I get the question that why don't we just go to higher frequency oscillators so that we don't have to go to very low temperatures. It just turns out that it's not so easy to work with much higher frequencies, and it's related to various technology issues, material issues. You can't get low loss oscillators because you have to make the capacitor, the dielectrics are involved. So it turns out that this 5 gigahertz, particularly the 4 to 8 gigahertz band, is very convenient from the point of microwave engineering, also from the point of view of all the control electronics, which is easily available and stable, low cost and good quality. So this is the reason why these parameters are chosen in this range. Okay. Now, one of the nice things about the superconducting circuit architecture is that it really gives you a lot of freedom to design your qubit. Essentially, there are 3 building blocks: Josephson junction and the capacitor I already introduced, but you can also introduce a linear inductor as shown here. And by combining these 3 elements in different circuit topologies and different ways, you can basically create a different potential energy profile, which means a different quantized number of energy levels. And then depending on exactly what you're trying to do, you can construct this. So it's really flexible. You can be very creative with this. And over the years, you have a lot of different qubit designs. Some of these are shown here. The one I showed earlier is the transmon qubit, which comes here, which does not have a linear inductor. So it means, in this picture, because it's in parallel, that it's a limit L tending to infinity, and this axis is Lj over L. So it's at the value close to 0. And then this one talks about the capacitive energy. So in this review article from 2013, this is sort of like an artificial, so it's like a periodic table of artificial atoms. So these devices are often called artificial atoms because they recreate an energy level structure like an atom, which can be then used as your quantum states. But they're artificial, of course, because you're making them out of electrical circuits. So there are various different designs. The transmon is the most popular one, and it is the design which is used in the IBM and the Google systems. But another one called the fluxonium is emerging quite strongly in the recent years. Now, one of the big advantages of this is that it's a lot more nonlinear. So if you remember, in the transmon, all the energy levels were fairly close by, even though they were different. In the fluxonium, after the first two levels, the next highest level is quite high, far away from. So that has some advantages in terms of how quickly you can manipulate the quantum system. So, and then, you never know, tomorrow somebody could invent a new, in our own lab at TIFR, we have been inventing new kinds of qubits and trying to understand whether they offer any advantages compared to the existing designs. And in order to make this, there are, sort of three key basic steps. I don't have the time to go into the detail, but essentially first you have to design the circuit and you have to simulate it. And this typically involves understanding the microwave properties using finite element simulations. And then you use something called electron beam lithography to make those very small structures. Even though the overall device here was quite big, the Josephson junctions are actually much smaller. They are of the order of a few hundred nanometers. So you need to have very fine lithography techniques using electron beams. And that's what you use. And then you have to do metal deposition to get the aluminum in the right places to form the structure you are trying to make. Okay. So let's now move on to how one creates interactions. So you have now two of these qubits, and remember these are LC oscillators. So how does one create an interaction between them? It's actually very simple. You can just put a capacitor between them, and now these two electrical oscillators are coupled to each other. So you can really think of them as coupled oscillators or coupled pendulums. And I'm sure some of you have done or seen experiments of coupled pendulum where you oscillate one of them and then the other one exchanges energy back and forth between them. So very similar physics allows you to create interactions, and that physics can be used to do these so-called 2-qubit gates. And it's actually very important because without this ability, you cannot create what are called entangled states. So you need these at least 2-qubit interactions to create entangled states, which form an important class of states for quantum computing. And they're actually the more non-trivial multi-qubit states. Instead of a capacitor, you can also use a microwave resonator. So here's a picture from a paper from IBM from many years back. You have these two qubits here, which are these, what you're seeing are the capacitor pads, and they're connected with this meandering line. This is basically a microwave transmission line, which allows you to keep the qubits far, they are like few millimeters apart, rather than right next to each other if you wanted to put a sort of an effective capacitance between them. So this allows you to place them out. So this is often called a bus cavity, which creates coupling. But this is a fixed coupling that once you design it, this coupling strength is fixed. But you can also design more complicated circuits like the one shown here from John Martinez group from, again, a while back. Here, the capacitor shapes are different. They are these plus type shapes, but effectively it's the same thing. The shape here is just to make it connect to different things which are coming from various sides. And then this thing in the middle is a circuit made again using those junctions, and that allows you to actually control the coupling, which means that I can turn it on and turn it off at will by passing a current through this circuit. So this is just to give a flavor that you can have fixed coupling, you can have tunable coupling, and they all have their pros and cons depending on what you're trying to do. Okay. Then finally, the most important aspect is the measurement as well. I say most important. because I spent a lot of my PhD and postdoc working on this problem on how to improve measurements. And this might seem like a trivial thing, but it turns out that because these systems are so fragile, measuring them efficiently without destroying them or destroying the state or corrupting the state is not so easy. You have to do it in the right way, in a very sensitive and fragile fashion. And an architecture which was developed called the circuit QED architecture really allows you to implement this textbook quantum measurement. And so here's what the circuit is. So here is your qubit, which is your nonlinear oscillator. And in order to measure it, you actually couple it to a linear LC oscillator, which is often called a cavity. So the two are coupled. So this again looks like the coupled oscillator I showed you in the previous slide for two qubits coupling to each other. But here the qubits and the cavity are nonlinear and linear oscillators respectively. Secondly, the frequencies of the qubit and the cavities oscillators are different by design. Whereas in the case of the two qubits coupling, they have to be close to each other at least so that they can interact. Here, the interaction is sort of perturbative. And what that does is that if you now sort of write down the Hamiltonian, you don't really have to worry about this, but effectively the Hamiltonian here is written as a spin half, which is a two-level system to represent the qubit, and a harmonic oscillator to represent this cavity. But because of the interaction between the two, a perturbative interaction, you get this term here, which tells you that the resonant frequency of this cavity is now dependent on the state of the quantum system. So depending on whether the qubit is in the ground or the excited state, the cavity will have two different values of frequencies, and depends on this value chi, which is sort of proportional to this quantity g square over delta. G is related to this capacitance, how strongly they are coupled to each other. And delta is the difference in the frequency of the qubit and the cavity. And it's important that they are different, otherwise the qubit states will get manipulated even if you don't put in any cavity, energy into the cavity. And this basically means that in order to know the state of the qubit, you have to measure the resonant frequency of the cavity. So this resonance can look something like this. So these are two resonance curves. They're slightly atypical. Most of you might have seen a resonance curve which looks like a peak or a dip, but this is because these are lossless systems. They don't absorb any energy. So when you send a microwave to them, they just come back without any change in amplitude, but they have a change in phase. So what you look at is the difference in the phase and what is going in and what is coming out. And you have two curves slightly shifted, one corresponding to the ground state in blue and one corresponding to the excited state in red. And then you choose a frequency here somewhere in the middle where this phase difference is as large as possible. And that basically is what you detect. It allows you to implement a textbook quantum measurement. And by textbook quantum measurement, I mean what I described some slides ago, that if I measure a two-level system, I should get the answer 0 and 1 corresponding to the probabilities of that particular superposition. And not just that, but after the measurement, the final state of that quantum system should become equal to the corresponding eigenvalue you measured. So if I measured 0, the quantum state should end up in state 0 and vice versa. And this Hamiltonian allows you to do that up to some approximation. That's been very, very successful. Now, in order to detect these very tiny phase shifts, well, the phase shifts can be big, but the power you send in is actually very, very small. As I said, these systems are very fragile. You have to do this very carefully, and you have to use very specialized amplifiers and detection systems, but it's possible to measure them very, very precisely. What you're seeing here are histograms of the phase measurement for the qubit being in the ground in the excited state. So the x-axis here is some arbitrary unit, but it's basically, you can think of that as a phase shift. So you can see that these blue curve and the red curve have two main peaks. They're centered at different values, around 80 and 160. So those are the two mean values. And there's a distribution of values. That's just because of noise. You have a distribution. And you have to notice that this is plotted on a log scale. So these two are actually very widely separated, which means that the error, which comes from the fact that you might accidentally interpret 0 as 1 and 1 as 0, this comes from these crossing lines here. But you also see these extra bumps here. So what I mean by that is if you look at the blue curve, it should ideally be centered around this point. But there is another set of distribution, which is much lower in value, 2 orders of magnitude lower, but it's centered around the one state and vice versa. And this is one of the challenges which people have been working on, is that when you do the measurement, the state can change. So the ground state can end up in the excited state, and the excited state can end up in the ground state. And that also gives you error because you make a mistake in reading the answer. So this 98.86% fidelity basically tells you how accurately you're doing this measurement, that if I prepare 0, I always measure 0, or prepare 1, I always measure 1. That would be 100% fidelity. But this tells you that, some 1.1% or so error happens. And this is something that needs to be improved. And, people have now done fidelities in the excess of 99% and even higher. And this is again an important problem which we are also working on in our lab, trying to improve these numbers as high as possible, because ultimately you would like to get this as close as possible to 100%. Okay. But once you have these kind of measurement fidelities, you can actually see quantum states change in real time. So here are actually experimental curves where 6 different experiments where the system was initially prepared in the excited state, and that corresponds to this level here. Now, this is a different experimental setup. So here, this digitizer unit is like -40. And then you suddenly see that after some time scale, it jumps to the ground state. So this is actually really the artificial atom emitting a photon and relaxing to its ground state. So you can see this in real time. And these things are often also called as quantum jumps. So this kind of thing was, actually led to the Nobel Prize when this experiment was done in ion traps more than 30 years ago. And I was lucky to do this experiment in superconducting qubits for the first time during my postdoctoral days at UC Berkeley. So, but this data is actually from our own lab at TIFR. So these are really high quality measurement processes. Okay, so that was the measurement. How does one actually control? So I had mentioned this in passing a little while back, that you have to send in electromagnetic radiation, which is resonant with this transition between the ground and the excited state. And that's basically what it is. You send a microwave pulse at this frequency omega-01 of a certain amplitude and a certain time. What this does is that it induces a phenomena called Rabi oscillations. And to study that, what you do is you basically send a pulse and you make a measurement. So remember that pulse, the control is also a microwave pulse, but now at the qubit frequency, and the measurement is also a microwave pulse, but at the cavity frequency. Right? These two are different earlier. And then you look at what happens to the measurement as a function of the length of this pulse. And that's what's plotted here. So what's plotted here is the probability of finding the system in the excited state as a function of this pulse length. And that oscillates sinusoidally like shown here, and then slowly decays to this value over a large time scale. And this is because of decoherence. If there was no decoherence, this would be a perfect oscillation from 0 to 1 and will keep going back and forth. Okay, so this is an example of driven two-level system physics. And it's this you can use to control, because what is happening between 0 and 1, all of these in-between states are superposition states. Because actually in this picture of Bloch sphere, what you're changing is you're rotating the vector from one value to another value. So the amplitude of the pulse controls how fast these oscillations happen. So how fast this vector will rotate along this. The phase of this microwave pulse determines the axis of rotation. So which means that I can rotate it along this axis or along that axis, depending on the phase of this microwave pulse. And then the amount of rotation is going to be given by the amount of the pulse you have used. So now you can sort of see that by controlling these three things, I can place the system from anywhere, starting from anywhere on the Bloch sphere to anywhere else, right? So these are essentially what are called single qubit operations, and essentially it relies on this phenomena of Rabi oscillations to achieve it. Okay. To create these pulses, you have to use basic techniques of modulation, demodulation. I mean, this is more on the technical side, but I thought I would give you a flavor of what actually goes on to create these pulses. So the goal here is to create a microwave pulse of varying amplitude and phase, and which means that you want to create some signal which looks like this. So it has some frequency omega t, often you call the carrier, and it has some amplitude varying with time, and a phase which might be varying in time. You can break this up into its sine and cosine components using a trigonometric simple identity, sine A plus B. And then These are often the terms proportional to sine omega t and the terms proportional to cos omega t are often called the in phase and quadrature phase amplitudes. So I of t and Q of t. So this is a generic way of writing this kind of a function in another way. So instead of a sine omega t plus phi, you can write I sine omega t plus Q sine omega t. And by controlling I of t and Q of t is equivalent to controlling amplitude and phase. And it's written in this way because we have a device which allows you to do this, because remember what you're doing is you're multiplying sine omega t with I of t. You're multiplying cos omega of t with Q of t. So the sine of t is created with a microwave source so that you can set the frequency omega and it will oscillate. I of t and Q of t are created using these what are called arbitrary waveform generators, which can create any voltage as a function of time, with some sampling interval. And then these go into a mixer. And this mixer is a device, it's actually based on diodes, which allows you to do this operation, I of t multiplied by sine omega of t and Q of t multiplied by cos omega of t. And that's what you get at the output. So this is how you actually create the physical pulses which control your qubit. So this is specifically called an IQ mixer for modulation. And the same process can be done in reverse, because remember that the measurement, I had told you that what you're really looking at, you're detecting a phase shift. So there the problem is that you have a signal which can either have phi 1 or phi 2, and you want to know the difference between them. So you can again translate that into this thing and say that, okay, I really want to know a difference between I and Q, which will have one value for one state and a different value for another state. So this process can be done in reverse to go from this signal to individual I and Q, as opposed to going from I and Q up to the signal. And so use the same mixers for demodulation as well. So some of you who are familiar with how radio transmission works, this is very, very similar, just at a different frequency. Or even your cell phone, when our voice gets modulated onto a carrier, it goes to the other person and then it gets demodulated on the other end and gets converted back into sound. So it's exactly the same idea, but just at different frequencies for both the carrier and the modulating signal. Okay, so that's the sort of the technical part of how the signals are generated. To give you a sense of how complicated or what really goes on to really measure a single qubit. So here it's actually shows a 3-qubit system. There are 3 microwave sources at frequencies omega A, omega B, omega C. There are 3 mixers. So these circles with crosses is a symbol for mixer. There are these arbitrary waveform generators. Then the output is all combined using what are called power combiners and then sent to the device. And then from the device, it comes back and then it gets demodulated and the outputs are sent to a digitizer, which converts them into digital form, and then you can process it. So this is sort of roughly the basic setup. On a lab rack, it looks like this. So here are some arbitrary waveform generators. There are some microwave sources here, and they're all connected with cables, with microwave cables, which are coaxial cables as well. Here is a picture of the fridge where the experiments are done. So this thing on the left here is the dilution refrigerator, and the different plates reach different temperature. And the lowest plate here, this is the one which reaches 10 millikelvin. So you just attach all your experiments to this. Your experiments are basically in different kinds of metallic boxes in copper or aluminum. And that then also reaches the same temperature. In order to do the control and measurement, you need lots of microwave wiring, which comes from the top all the way down. These are all specialized microwave cabling. They have to be thermally isolating so that they don't put a lot of heat load to the fridge. They have to be filtered with specialized filters. We have to shield them from magnetic noise. And of course, you have to make the devices and package them. So these are all the different things which goes into doing these kind of experiments. So the idea here is to just give you a flavor for the different parts here. So you have to do all kinds of microengineering, cryogenic filtering to get these experiments to work. And you have to really protect them from all kinds of external noise as well. Okay, so inside the fridge also there's a lot of complicated wiring, because these lines can bring noise from room temperature. So you have to put attenuators to reduce the noise as they come down and then go to the device. And then there are special devices which called circulators, which allow signals to flow only in one direction. So the signal comes like this, and then from here it goes to the device, and from the device it comes back up with a phase shift, and then it goes to a different line where it first gets amplified using specialized superconducting amplifiers and then goes back up. And then you have to amplify them again so that the signal is big enough for you to detect it. So you have lots of attenuators, reflective filters, lossy filters, circulators and isolators, cryogenic amplifiers, magnetic flux lines for tuning, and all of them are connected with coaxial cables. So this here is just the setup to control and measure one qubit. And if I expand it out, here is the wiring diagram for a 4-qubit experiment, sort of identically duplicated. So one of the challenges, of course, is that as the number of qubits rises, how many of these components can you pack, into a dilution refrigerator? So people are coming up with various tricks to reduce the number of wires that is needed. So for example, you can use the same output line for many qubits if you use something called frequency domain multiplexing. So use slightly qubits if you use something called frequency domain multiplexing. So use slightly different frequencies for the different measurement cavities, and you can combine them into one line. So at least one half of the circuit doesn't have to be duplicated. But of course, you can't multiplex in infinite number of qubit or even thousands of qubits. So you have to do it in batches maybe. So this is a technique which is often used. So I just wanted to show you that, there's all kinds of things, different flavors, different topics which go into building a system like this. So in the last 10 to 15 minutes, I just want to give you a flavor for what happens when you have all of this ready. How do you characterize the systems? The first thing you do is you do what is called spectroscopy. That means you first need to find out what is the qubit frequencies. You design them to be a certain value, but they will never come out exactly the same. So you need to measure it. And this is basically done by sending a microwave frequency tone at the cavity frequency to detect the state. And then you sweep the qubit frequency tone. And then essentially you see when it becomes resonant, and that gives you a dip in the signal. So this is some data from a 3-qubit device where there are 3 qubits at around 4.5, 5.35, and 6.15. And you see these dips here, and these broader dips correspond to the 0-1 transition. But in addition, you also have these very sharp dips right next to them. And this actually corresponds to omega 0-2. So it's a 0 to 2 transition, but a 2-photon transition. So this actually is 0.2 divided by 2 over here. So by noting down the position of these two numbers, I get the values of the first transition and the second transition. So I really know if my qubit has come out right, where is it, so that I can now do the manipulation and things like that, right? So this is what you do first. Then once you have these frequencies, you can calibrate the pulses. And this I already explained to you earlier. This is done using the Rabi oscillation experiment. So if I now zoom into this first oscillation, what it tells me is that for a given amplitude of the microwave pulse, I need to choose a time which is equal to this, so that I can go all the way from ground state to the excited state. And this particular pulse is called a pi pulse because it rotates the block vector by an angle pi and takes ground state to excited state or excited state to ground state. But if I go exactly halfway, then this is called pi by 2 pulse. And this will allow me to go from ground state to the middle point, which is the equal superposition state. So these kind of calibrations you have to do. You have to measure the length, adjust the length or the amplitude very precisely so that you're exactly at these points. And only then you can get very accurate manipulations. So once you know how to make a pi pulse, you can now start measuring the decoherence properties. And one of the first things you do is measure what's called the relaxation time. And this is basically the time for the system to go from the excited state to the ground state. So you put a pi pulse, then you wait for some time, and then you measure. So if the wait time is 0, of course, you have made a pi pulse, so the system will be found in the excited state. So that's where the curve starts. But as you wait longer and longer, in between the pi pulse and the measurement, the qubit could have decayed to the ground state because of finite coherence and basically, remember, oscillator dissipation. And then what you see is that on an average, this probability decays exponentially. So each point here is a repetition of many, many such measurements, because remember that each measurement gives you 0 or 1, and you have to then average it to get the probability. So these are called ensemble measurements. And then you just plot this average probability as a function of this delay time, and you get an exponential thing. By fitting to this, you get what is called the T1 time. right? And of course, this is the average. I already showed you what happens in the real time where you see these quantum jumps. But if you average all of them, you'll get the exponential again. So these are the two pictures of single experiments on single quantum systems with each individual measurement versus ensemble measurements, which give you the average property or the average behavior of these systems. Okay, so this is how you get the T1 time. Then another important time is the dephasing time. And this is related to the fact I told you that if you make a superposition state, the phase phi can also get randomized. And this happens also due to environmental noise. And in order to measure that, you use a protocol for measuring what's called Ramsey fringes. So there you actually use 2 pi/2 pulses, which are spaced by time delta tau, and then measured. So again, if delta tau was 0, these are 2 pi/2 pulses, one after the other, which means it's effectively a pi pulse. So you start in the excited state. And then as the time delay changes, these things oscillate and again decay. And by looking at this decay curve, you know how quickly the phase is getting randomized between the 2 pi/2 pulses. So this is what decoherence does. And from these measurements, you can extract this quantity T2, which actually includes this dephasing process and also the T1 process. Because if in between the qubit also decays, that also prevents this oscillation from continuing. So you actually get a combination like this. And from that, you can extract the pure dephasing time because you already know the T1 time. So by measuring T2 and knowing T1, you can extract T5. So this now sort of completes the characterization. You know how to make the pulses, you know the decoherence time. So you can now go and do other things, which in a multi-qubit system would involve basically running some kind of a quantum algorithm. And from what I have told you, essentially every gate, like every single qubit operation or a 2-qubit operation, even though we didn't go into detail on the 2-qubit operations, is essentially a microwave pulse. So each gate is a microwave pulse with a specific characteristic, shape, size, frequency, time. And then they have to be calibrated to make sure that they are doing exactly the operation they are designed to. And this, you have to do this periodically because these parameters can drift, your electronics can drift. So you have to do it continuously to keep the overall accuracy of your algorithm implementation properly. Okay. So once the basic elements are there, you need to be able to do this over many, many qubits. And here are some multi-qubit chips. These are fairly old now. This is a 9-qubit chips from Google and University of California, Santa Barbara. This is a 16-qubit chip from IBM. And of course, many of you have seen this 53-qubit chip from Google. And you have to basically follow these principles and make them larger and larger and be able to control a lot of them. So where we stand now is that we sort of understand the basic building block, the single qubit, really well, but it's not perfect, in the sense that the coherence could still be improved further, the measurement fidelity could be still improved further, how it interacts with other qubits could be improved. And if you really want to scale, that means to make a system with large number of qubits so you need a lot of resources, you need high-end fabrication, you need lots of electronics and engineering to make this electronics work properly on a large scale, and also in a practical, efficient way. Right now, if you just copy the number of things you need for 1 qubit for 1,000 qubits, it would be not practical. So new kinds of electronic devices and things, and all of this is happening. So you have to make scalable electronics, make the basic blocks more robust, and also work on the interconnectivity architecture. This is related to how the qubits can actually talk to each other, which qubit can talk to which other qubit in this network. Because typically these are laid out on a 2D surface, often the qubits can only interact with nearest neighbors. And it turns out that sometimes having qubits interact with too many qubits can also give rise to other kinds of errors called coherent errors. And then finally, so these have to be balanced out. And Google and IBM have taken slightly different approaches. Google has used tunable couplers, and IBM so far has only used fixed couplers, the things I mentioned right at the beginning. But in a recent announcement, they said that they are also going to move to tunable couplers. And that really seems to be the future, because you really want to turn the coupling off when you're not doing 2-qubit gates. And a very important milestone for the future for all architectures is what is called quantum error correction. I won't have time to discuss this, but just to tell you very quickly that even though these unstable processes, these decoherence processes which make the qubits unstable are happening, it turns out that if you use a collection of a certain number of qubits which are individually bad, but you can use them to collectively store the information of one qubit amongst multiple qubits. And if you do that in a very clever way, it turns out you can actually detect that a decoherence process related error has happened, and you can fix it, and you can recover the state. And that uses quantum entanglement in a big way. And this is a big milestone and a very important step in order for these systems to become practical. None of the quantum processes available today use quantum error correction. So there have been many demonstrations that this idea works in general. To end, just a few big highlights. I'm sure many of you have seen this race towards quantum advantage. What is quantum advantage? It's the point where a quantum computer is able to do something which even the most powerful classical computer on earth can do. Okay, doesn't matter whether that problem is useful or not. And in this case, these are some mathematically constructed or artificially constructed problems. But in 2019, Google claimed that they, using 53 qubits, they were able to show that a problem they solved in 200 seconds, which they estimated that even the most powerful supercomputer on Earth would take about 10,000 years. Of course, we can't verify that, but it's an estimate based on calculation. More recently, several groups in China working together made a different qubit processor, which has 56 qubits, and it's a similar problem. And they claim that their system could do a problem in 1.2 hours, which a supercomputer would have taken about 8 years. So slightly less modest, but still very impressive. And they seem to have solved some of the loopholes which are present in the first experiment. And there have been similar demonstrations in other systems as well, not superconducting qubits, but using photonic quantum processes. Okay, and I'm sure, as many of you know, quantum computers are already available, many of them for free to access online through various cloud resources from Amazon, IBM, and Microsoft. And I just want to point out that Indian scientists are also building quantum computers and other quantum technologies. I'm working on a project where we'll be building a 7-qubit system, and hopefully in about a year's time we will have that working. So that's basically it. So I want to stop here and summarize. I introduced the idea of qubits as two-level systems and the block sphere representation. Then we talked about how superconducting electrical circuits can be used to make these qubits, or artificial atoms as they are sometimes called. We talked about the qubit design and properties, how to do the control and measurement, and then these major milestones achieved. And as I mentioned right in the beginning, there are several superconducting qubit projects underway in India at TIFR Bombay and IISc in Bangalore, and funded by these various agencies like DST and MIT and DRDO and DE. So let me stop there, and thank you for your attention. I'm happy to take questions.
Yeah, Subhash, please go ahead.
Thank you, Professor, for such a nice pedagogical talk. Maybe it's a vague question, but I was wondering the possibility of time multiplexing as an option of scalability for superconducting systems.
Time multiplexing, yeah, that's a good question. It's definitely possible. For steps where the this multiplexing aspect I was discussing is particularly related to the measurement aspect. So if the measurements don't have to be done in any particular order, one can actually use that. But usually time domain multiplexing would mean that there is some kind of a mechanism, and especially in this case, because this is happening at the cryogenic level, you will need some system which switches the signal from one to the other as time proceeds, in some kind of a clock fashion. And that will have to be done cryogenically. And I think I vaguely remember that one group had proposed some architecture and maybe even demonstrated some proof of principle. It's definitely possible, but one has to really look at the particular scenario where this will have to be implemented to achieve that. But the way the experiments are done these days is that we often wait a long time before repeating the experiments, because we wait for the system to relax to its ground state, and which means that you have a lot of dead time. And there in the dead time, you can really use the time multiplexing to measure different qubits at different times by using the same resources at room temperature, for example, if that's something you want to do. But yeah, it's a possibility.
Thank you.
About other questions?
I see some question in the chat. Is H dispersive A dagger represent the bosonic annihilation creation? Yes, yes. They are the standard raising and lowering operators for the harmonic oscillator.
Maybe I'll just go for one more quick question.
Sure.
It's regarding the tunable coupler that you mentioned. The tunable couplers, are they in some way equivalent to like variable beam splitters in optics?
Not exactly. One could imagine building something like that, but it's actually very a lot more simple than that. Let me go to that slide. Yeah. So let's just look at the image on the top where I'd shown this simple picture of two capacitors, connecting these two circuits. What does a tunable coupler essentially mean? Is that if this was a variable capacitor, right, then I could make that capacitance value very small, and then that means the coupling would be very small or off, right? Here, it actually is playing with a network of inductances. What it does is that one way of thinking about what coupling is doing is that if there is some excitation on qubit on the left, this coupling element transfers some of that energy to the qubit on the right. So that can be done using any electrical network. And here, the inductances are being controlled by using Josephson junctions. So remember, I told you that this is like an inductance, and if you have two in a loop, you can tune the value of the inductance. And you tune it in such a way that for particular values of the inductance, the amount of voltage transferred from one end to the other can be made exactly zero, like with some kind of a balanced circuit kind of picture. So that's really what is happening. And there are other more sophisticated techniques. So in this picture here, towards the end, excuse me. Yeah, this picture towards the end here, this is actually the architecture. Excuse me. Sorry, my sneezes finally returned at the end. If you look at this thing, it says qubit 1, qubit 2, and coupler, but all the three circuits look exactly the same. And in fact, they are. So what has happening here is that the middle thing is also a qubit, but by changing its frequency with respect to the first one, it creates an effective interference between the signal paths going from left to right. So it can cancel that exactly and give you a point of zero coupling. So that's another way. So here it's sort of some multi-path interference. Beam splitter, is more. It's difficult to imagine a parallel from optics to here, but this is sort of a few of the ways tunable couplers are built. It's really, you can think of this completely classically for most of the cases. Here, the interference effect is a little bit subtle because there's some quantum thing involved because of the multiple levels of the coupler as well.
All right, thank you very much.
QIQT, please go ahead.
Hello.
Yeah.
Sir, since you talked in beginning about the superconducting circuits, I want to know that people that are working on bound Majorana states, like how that system is different from the one discussed here.
Okay, that's a great question. The bound Majorana system also uses superconductors, but in a very, very different way. Okay, so here the superconductors are being used to create electrical circuits with very low dissipation, right, and some nonlinearity. What's happening in the Majorana bound state is that you're using a combination of a superconductor and a semiconductor, and in that interface, you are hoping to create these specialized states, so-called Majorana states. And those states have a completely different property, that they are topologically protected from noise of the environment. So superconductivity is being used, but it's a completely different field. The physics of what the qubit is, the physics of how the qubit states are changed, what affects the coherence times and things like that are completely different. So there is really no straightforward overlap between the two fields.
Are there any more questions? If not, let's thank them. Very, nice talk, very enjoyable talk. I really enjoyed it.
Thank you so much.
Every time from your group, there are new results. So
Yeah.
thank you so much.
Thanks. Bye-bye.